Excellent. So, as I said, the way we're going to start today's course is sort of finishing the discussion that we were having on practical data mining and how you actually analyze a data set that we finished with last week. And I thought that it would be sensible for us to try and have a sort of interactive experience or sort of a play together with a particular data set in an attempt to sort of get you guys familiar with how one goes about actually doing data mining in a practical sense. And so the way in which I've set this up is, as you might remember from last week, I've constructed a data set, or rather I've got a data set from online. And that data set, as I said last week, is, I think, highly relevant to all people studying physics and astronomy living in Germany in 2021. And that data set is of pizza sizes from 2 Australian restaurants in 2012. And basically what we're going to do is we're going to go through this data set knowing nothing about it from the beginning and try and extract the information that we want so that we can make an informed choice about which pizza to select and which restaurant to order from. And so the way in which we're going to do this, the way in which this is going to be sort of interactive, is I've created something of a choose your own adventure. And for those of you who aren't familiar with that concept, these are the sorts of novels where you get to a particular page and it says you can turn left or turn right, and if you turn left, go to page such and such. If you turn right, go to a different page. Now, I've set up the same sort of thing within these slides. So when you go to this particular slide deck on the slides, what you'll find on Moodle, what you'll find is that I've got all of these options here. And instead of navigating through these slides like you would a normal slide deck, instead you navigate via the little options. And you'll see what I mean. And the way in which we're going to make this interactive is that we're going to have, there's a question that's popped up. Will the data set be on Moodle? Yes, I can absolutely pop the data set up on Moodle. That shouldn't be a problem at all. And then you can go through and do exactly the same sorts of exercises that I've done here and play with it yourself. So yes, absolutely. That's a great idea. I'll make sure that I upload the data set alongside the lecture notes and the recording. Great idea. Okay, so the way in which we're going to sort of engage with this is, I've got my little poll here that I've just called Choose Your Own Adventure. And now the way in which we're going to go about this is you all have the ability to vote for an option 1, 2, or 3 at any point during the discussion. And as you can see, as you vote, the options will come up and we'll essentially go with the group opinion. And so you can see I've given you an example here, and the example is you're walking out through the forest and you come across a small cottage made entirely out of candy. What do you do? Option 1, do you go inside and discuss with the person, the merits of bricks and mortar? Or option 2, do you take a photo for Instagram? Option 3, do you say, I'm smart enough not to go near the creepy house made of candy and therefore leave and keep walking? So we have online 22 people and we have 11, 12-ish votes coming through. So I think what we'll do is I'll try and have sort of order, I'll wait till there's sort of order 15 odd votes or if people are giving more votes, then we'll wait for the full group. And then we'll make a decision. So it looks like we've plateaued out here with going inside to discuss the merits of bricks and mortar. Option 2, making a strong recovery, but let's go with go inside and discuss the merits of bricks and mortar. And I'm very, very happy to see that option because it demonstrates that none of you are unfairly judging somebody based on their housing, which I think is the right attitude to have in 2021, really. And lo and behold, going inside leads to winning a Nobel Prize. So very, very unusual. So it says after, as I said, not deciding to unfairly judge somebody's house based on just the house itself, you're greeted by an educated lady who has a very lengthy discussion with you about the little understood merits of using candy for sustainable housing. And with your expertise and her ability at constructing houses made of candy, you both pioneer a new form of sustainable housing that revolutionizes impoverished communities all over the world. So congratulations to all of you for making a smart choice and indeed for doing what I think was the correct thing. So that gives you a rough idea of what this is going to be like. You guys can go back through and look at the other options and things of our little game here, on your own time. And the way in which we do this is then I'm going to go and I'm going to restart this poll so I can reset the results. And then when we come to the next poll, then you have the ability to vote again. So that's how we're going to do it. Hopefully that's clear, and hopefully you guys enjoy a little bit of more of an interactive spin. Don't worry, at the very end of this lecture, there's going to be another poll, which is, do you think this was good, bad, or et cetera, waste of time, whatever. So you'll be able to vote on whether or not you want to see more interactive stuff like this, or whether you like just having a standard sort of lecture format. So that's something we'll start at the end. So let's get started. So the first step in what we're calling mining pizzas, or rather data mining pizzas, we're going to be presented. We're being presented with a data set that has that all you know is it's a data set about pizza from Australia in 2012. You don't know anything else about it. And you have these three options that I've given you. You can either ask the question, what columns do the data have? You can ask the question, how many observations are there in the data? So you'll recall that we had, what we mean by observations from the last couple of lectures. Or you can ask the question, what is the average? And so we're up to 11 votes. So give your votes in now, and we'll make a decision about what to do. It looks like option 1 is making a fairly strong showing. Okay, we're at sort of 13, 14. Okay, looks like option 1 is going to win here. So let's do that. And again, you've all done very well, because I reckon that this is the correct thing to ask. So I think that when provided with a data set, it's always sensible. The very first thing to ask is, what is the format of the data in which we are presented with? Because that's going to dictate the types of analyses that we do later on. And so what we do first is we look at this data set and we say, okay, let me just take the column names of my data frame. So let me see what are the actual columns that I've got in this data frame. You can see that I've got restaurant, base, topping, and diameter. So all the sort of important information that you want to have when you're trying to make a decision about what pizza to order. Another option for looking at the actual data frame is to just look at the first n entries of the data. And so that's what I've done here by just taking the head, which prints the very top 6 rows of the data. And you can see that the restaurant here is of type character, as is the base and as is the topping, and then the diameter is of type double, so of a numeric type. And you can see that there's different values for here. So it looks like restaurant tends to be Domino's. The bases here tend to vary a little bit, and the toppings here tend to vary a little bit as well. And the last way that you can analyze or you can sort of learn what is in the data set in sort of a summary sort of way is, I personally think, the best way to do it, which is by using this str function that we've seen before. This is the structure function. And what the structure function does is it tells you the structure of the object that you're looking at. So I'm just going to expand that out a little bit. And so you can see that the data frame that we're looking at is of class data table data frame. It has 250 observations. So we've actually learned how many observations there are in the data by doing this structure thing. We know that there are 4 variables, and those 4 variables are named restaurant, base, topping, and diameter. They're of type character, and you get a sample of the values of those columns as well. So personally, I think that this is the best option when you want to learn a little bit about your data frame. And so looking at the structure of the data is probably the best thing to do. Okay. So we've learned that there are 3 qualitative variables here because they're character type. Character types are always qualitative. And there's 1 quantitative variable, which is of numeric type, and we've got 250 observations. Now, it's not necessarily clear whether or not the qualitative variables are nominal or ordinal, i.e. whether they can be ranked even though they're qualitative or not. And that's something that we're probably going to have to look at in a little bit of detail going forward. Okay, so that was good. Let's go to the next the next step. I need to move myself out of the way. So we're going to reset the results again, and we're going to go to the next step in the process. So the next step in the process is to pick a variable that we want to analyze first. So we have, we've got a few different options. I've sort of split these into what I think of the type of personality types that people would be interested in, or people would be, for selecting their particular choices. So we can have the savvy restaurateur who wants to know what type of restaurants are available to us, the discerning critic who is interested in knowing the types of toppings and bases that are available, or the value seeker, person who just wants to jump straight in and look at the diameters of these pizzas and make that as their decision. So we've got 13 votes. Looks like there's a strong push towards both the critic and the value. It looks like the critic is going to be winning out here. Okay, so we got 17 in. We said that was our threshold. So let's go with the discerning critic. So we're going to start out here by looking at the bases and toppings. So the first thing we can do is, because we have this qualitative data, you'll remember that when we have qualitative data, the way in which we analyze that is using this frequency analysis, which we can do just by tabulating the number of entries of all of the different data sets. And you can see that if we look at the base, if we tabulate the bases of the different pizzas that are in our data set, then we get these options. We have classic, deep pan, mid crust, thin crust, and thin and crispy. Now, these are, I would say, quite clearly an ordinal data set. That is to say that even though they are qualitative data, you can quite clearly rank these in a meaningful way. That is to say, you can go from thin to thick, or vice versa, from thick to thin, but there is a sensible way in which you could rank these data. Therefore, they are ordinal, just so you remember. It's also worth noting that there's something that we can learn, or a couple of things that we can learn here from the data set. The first of which is by looking at the absolute frequencies of these different things. It's quite clear that, okay, the deep pan here has the highest frequency, has 83 odd entries, and that the others tend to be around half that number. Okay, but it's worth also noting that there appears to be some sort of overlap between these possible values, right? So it's not just a simple data set of one of these things means deep, or thick, one of these things means thin, and one of these things means the middle, because arguably thin crust and thin and crispy probably mean the same thing. And that then suggests that maybe there's something else going on in the background that we don't quite understand yet. If we want to now look at the toppings, you see a similar sort of story. So again, we're looking at the toppings. We have barbecue, we have Hawaiian, and then super supreme and supreme. Now, again, if you look at the absolute frequencies of these things, both the barbecue and the Hawaiian have the same rough number of entries, of 80 odd entries. But these two, which again are similar in name, split the difference at 40 each. So again, perhaps something that's going on in the background here. If we look at the relative frequency of these observations, this becomes a little bit clearer again. So again, we have about a third of the data set is deep pan, whereas 15% of the data set is split, variably between the other options. So if one was to rank these in terms of their, ordinal nature and go deep, classic and mid together, and then thin and thin together, then you would end up with a third of the data set, a third of the data set, and a third of the data set. So that's telling us something important about the data set. Okay, then probably there is a representative number of each option in the data set. And that's a very important thing to know when we're doing later analyses. Same sort of thing happens with the toppings when you do it by split. So again, you have a third of the data set, a third of the data set, and then a third of the data set being split in half by these two options. So there's of order twice the number of observations for these two things. And it looks like this is probably being caused because of some sort of artificial splitting in name that doesn't necessarily have a meaningful difference in these things at the end of within the data set. Could be important, question mark. Okay, so that was the discerning critic. That was the bases and the toppings. So now we're going to go to the second most option, which was the value seeker, which was basically asking us what diameters of the pieces, what can I learn about the diameters that are specified in the thing, in this catalog. Now, this then, because we now have a numeric data set, now we can start to ask questions about whether or not we want to go with looking at point statistics and dispersion statistics in number, or whether we want to do things, visually. So if we go back here, I'm going to reset the poll once more, and you can vote for whether or not you want to go through option 1 or option 2, whether you're interested in working with point statistics or you're interested in learning via the visualizations. Looks like the visualizations are winning out, which, arguably isn't surprising. Visualizations tend to be a very good way for identifying and understanding complex data. So we're going to go through the visualization route. And the first thing we're going to do is, because remember, we're looking at diameters, the first thing we're going to do is we're going to plot the diameters just as a histogram. And what do we learn? Well, the first thing that we learn is that the data is clearly very strongly bimodal. That is, that there are 2 populations here. Now, already you could start to think to yourself, does this have, you could start to infer some possible hypotheses in your mind, right? These could be the differences between the thin and thick base pizzas, right? Or this could be something to do with the restaurant that you're ordering from, right? Both totally valid possibilities, okay? The next options that we have is to say, okay, there's 2 peaks here. We now want to try and learn something about this data by delving deeper and looking at the data split in a visual way by diameter, looking at the diameter of the data split by some additional quantity. Okay, and that additional quantity could be restaurant, base, topping, right? Because those are the 3 things that we have in our data set. So resetting the results again, do we want to analyze, do we want to look next at the distribution of these data split by restaurant, by base, or by topping? Now, it's worth noting that one of the things we didn't look at yet is the restaurants. Remember, we skipped over that. So if we were being totally fair, we would say, okay, clearly restaurants are probably, the group here thinks that restaurants are important. So we probably should have gone back and looked at the format of the restaurant data. However, we can do that step at the same time as doing this next step in the analysis by calculating plotting the distribution of diameter just split by restaurant and letting the actual plotting device that we're using do that for us. So one of the utilities of doing data analysis in a language like R, a language like Python, is that you can make a hypothesis like, the overwhelming majority of us have just made, which is that this difference, this bimodality, is probably due to restaurant, and then say, okay, I don't want to go by hand and dig out and split the data by hand and then plot one plot and then plot another. Instead, what I can do is I can use the tools that are available to me within the programming language and do these sorts of plots directly, or do these splits directly. And so the way in which I've done that is, you'll remember the violin plot from last week. And I've plotted the violin plot, which, as you'll recall, is a combination of a kernel density estimate, which is the actual violin, and the box and whisker plot that I've overlaid on top. And the way in which I've plotted this and the way in which I've split this by restaurant, without knowing anything about the restaurant data itself, is simply by saying that I want to do a plot of the information contained within my data frame, and I want to split by restaurant on the x-axis and diameter on the y-axis. And then I want we'll look at what this fill does in a second. And so what have we learned? Well, first things first, what have we actually plotted here? Well, we've plotted the distribution of diameter given the value of restaurant. Okay, and this is a very, very important property or thing in statistics. What this is called it's called the conditional distribution. So the conditional distribution of a variable is the distribution of any variable given the value of a second variable. Okay, and that's going to be very, very important when we start looking at probability, both later today, but most likely next week when we get to conditional distributions. So what have we learned here? Well, the first thing we've learned is that firstly, there are two restaurants in the data set. One of them is Domino's. The other one is a restaurant called Eagle Boys, which I don't think exists outside of Australia. So I doubt anyone has ever heard of it. And the first thing that we can notice is that if you now look at the distribution of diameter as a function of restaurant, the Domino's restaurant clearly has bimodality here. So there's clearly some additional complexity coming into the Domino's data set that isn't probed just by splitting by restaurant, but that the Eagle Boys distribution, with the exception of this outlier here, is pretty strongly unimodal. And therefore, that if you were going to if you knew nothing else about this data set, if you had no more information, then you would say the median diameter given by the line in the box plot of a Domino's pizza is of order 68 units, which I'm now going to tell you is centimeters, which will horrify the most of you, I'm sure. And the Eagle Boys diameters have a median of 73 centimeters, which is a big pizza. And so this is really useful for us. This now tells us that if we had no other information and all we wanted to know about our pizza was whether I was going to get a big one or a smaller one, then you would probably go for Eagle Boys with no other information. Okay, but as I said, there's clearly some complexity here that's worth probing. So we can go back. We can go back to our distribution and we can say, okay, we just looked at the conditional distribution by restaurant, but that didn't fully explain the variance and the complexity within the data set. So what are we going to look at next? Well, we'll go back here, and the second vote that we had here was for option 2, and that's splitting by base. So let's make the same conditional distribution, but now instead of diameter conditioned on restaurant, let's do diameter conditioned on base. Okay, and what you see is that now we've again got some split in the diameters here. So looking at the classic crust, there's clearly a preference for those to be smaller pizzas. Okay, the deep pan tends to split bimodally as well. So again, clearly some complexity there that isn't captured in this conditional distribution. And the mid, thin, and thin and crispy are all larger. Now, with the exception of some outliers again. This then raises the question of, firstly, we haven't described all of the variance in the data because there's still some bimodality here in deep pan. And if it turns out that you were a fan of, thick pizzas, then you would want to explain this variance prior to ordering your pizza, right? If you were a fan of thin pizzas, you would probably say, well, I can't lose. And so you would order whichever one you wanted and you would be fairly happy with the outcome. Unless you were particularly picky and wanted to absolutely maximize your chance of getting an absolute behemoth of a pizza. Okay, so that's a useful conditional distribution. The last one here is split by topping, and nobody, or very, very few people voted for split by topping, which is arguably justified, but arguably, I mean, you should always explore all aspects of the data. So we'll look at that one as well. But you can see when you split by topping, you've got many items which are bimodal. Okay, so topping clearly doesn't have a strong correlation with the split that we're interested in separating out the bimodality of these data sets. Okay, so the conditional distribution of diameter with topping isn't super useful for us. So what's next? Well, there's clearly some important bimodalities in here that we still need to understand. There's clearly something going on with the restaurants, and there's also some added complexity in the base choice. Okay. So then the question becomes, how do we decide what to order, given that we know that there's complexity in there that we haven't analyzed yet? And the best thing to do is to then simply say, okay, what we want to do is try and identify the joint conditional distribution of diameter given base and restaurant. And this is where that fill value comes into that plot that I was just talking about. Because now, if we go to the last slide, what you can see is that I've now plotted the diameter conditioned on both base and restaurant. So I've got base on the x-axis here, diameter on the y-axis, and now the fill is splitting by restaurant. So you can see that I've got Domino's in orange and Eagle Boys in blue. And all of a sudden, some of the bimodality that we were seeing is clear. The origin of the bimodality is clear. So we said that when we split by base, we conditioned the diameter on base and we looked at the deep pan, there was a clear bimodality. And it turns out that bimodality is driven by restaurant, right? If you order a deep pan pizza from Domino's, that pizza is going to be, of order 8 centimeters smaller than the same pizza ordered at Eagle Boys. Okay. Conversely, if you were to order a thin and crispy pizza from either restaurant, it's not going to make a difference. And you can actually, and this also answers one of the things that we suspected earlier, which is what the difference between thin crust and thin and crispy is. It turns out that when you condition the base on the restaurant, you find out that thin crust only exists in Eagle Boys and thin and crispy only exists in Domino's. So it's clearly just a choice of naming that those restaurants use. Yeah. Okay, so we have this situation. We have arguably all of the information that we could possibly want extracted from the data set. If you were very interested in doing, you could also then split this in a different way by topping as well and have it conditioned on, for example, base and topping, knowing what you know about the two restaurants. Or you could say, using this information, there is no circumstance where Domino's gives me a larger pizza than Eagle Boys, given the base. And so I'm going to throw away Domino's as an option. And now I'm going to further identify the link between base and topping and figure out what topping and how they correlate and things like that. These are all additional things that you could do. But arguably, with this data set, you would now be able to make an informed choice about which pizza to order in Australia in 2012. So that's the practical data mining exercise. So you'll have access, as I said, you'll have access to these slides, and you can go through and look at different things, and you can, I'll give you the data set so you can reproduce these commands and look at the data in different ways as you like. But that's sort of the exercise, and I think that was good. I was aiming for about half an hour, so I think that worked out pretty well. Okay, so that's the interactive exercise. We're now going to switch to the next section of the lecture, which is all about probability, and you'll have to indulge me for 1 minute while this slide set compiles. And and then so we'll move on for the rest of this lecture. We're going to be talking about probability and the basics of probability and sort of what we can do with probability and how that ties in with our statistics. Cool. So thank you to everybody for for taking part in that. And as I said, towards the end, we'll ask about, oh, there was a lot of questions that popped up that I missed. Apologies. We will have a poll at the end for whether or not you thought that was useful or not. So I'll go through these questions now. My code is, the code that I showed there was all R. As I said in the first lecture, I'm very happy to give you examples of how you create these sorts of plots in Python using examples and stuff like I had in the zeroth lecture. If that's something that you would like, then please just give me that feedback and I can go through and make those things for you. Yeah. So the top, is there a way to get it to show base plus restaurant? Yeah, so this is the same, in that conditional argument that I had, you can just swap out any sort of option for plotting X. We had base, but it's easy to condition base on restaurant or just to plot the restaurant on the x-axis conditioned on base, et cetera, et cetera. So all that's totally flexible and it's very easy to do. And again, happy to provide examples of that. And in fact, I will. What I'll do is after the lecture, when these questions, I'll post these questions to the Moodle forum, like I've been doing for the last few lectures, and I'll provide some examples of what you can do. I'm very happy with this. Can we use not delicious data sets in the future? Some of us haven't had lunch. I'm one of those people who hasn't had lunch yet. And I'm also arguably the only person in this room who's ever had an Eagle Boys pizza. And I can tell you, if you know how good Eagle Boys pizzas are, this is much more painful for me than it is for you, I guarantee you. But yes, point taken. We'll try to use more non-food oriented data sets from here on out. And this is an excellent observation, the last point here, which is, wouldn't it make sense to combine the equal properties like thin and crispy, classic and mid crust? And that's absolutely one of the decisions that you can make when you do these sorts of analyses. So when you're provided, it's one of the super important things about doing data analysis is recognizing when you have unexpected redundancy between options in a data set. So the classic example of this is something that we don't come across very much in physics and astronomy. But in things like survey data, where you take surveys of, opinion or surveys of, mood and things like that, because synonyms are very, very common in language, it's very, very often that you get things that have the exact same meaning, but that are formulated very, very differently. And so you can absolutely get these sorts of things happening in quantitative data as well. And if you're interested, I can come up with some examples. But it is very, very important to be able to recognize when you have things that are labeled differently, but fundamentally mean the same thing in your data set. And so one way of dealing with that sort of occurrence is to do exactly what you've suggested, is to combine these things into a different variable class and just call it thin, or a different variable class and just call it medium, or something to that effect, right? Great question. Okay, so that's the end of the sort of data analysis or data description section of the course. And obviously this is all going to come back together at the end of the course in section 4, when we start talking about how we practically analyze and sort of usefully use all of the skills that we've learned so far to do good, accurate, robust statistical analysis. But for now, we're going to leave that behind and we're going to start looking at probability. Now, the rest of this lecture is going to be focused on basically the fundamentals of probability and some of the fundamentals, not certainly all of them, because we won't have time to get through them all. And so this will continue over the course of the next 3 weeks. So we're going to do this week and then 2 more weeks, probably at least, of probability. before we start moving on to the next section. So today, what we're going to be looking at is not actually decision theory, but rather we're going to be looking at the fundamentals of probability and sort of getting you familiar with probability, what it means, how you interpret probability, et cetera, et cetera, et cetera. Now, naturally, a lot of you will have an innate understanding of probability already, and that's just because we deal with probability on a day-to-day basis, whether we recognize it or not. And one of the points of this section of the course is basically to demonstrate that while you definitely have an innate understanding of probability, your gut about probability is most likely very bad. And that's not a judgment on any person, it's a judgment on how we think and how we interpret things and how our brain functions for day-to-day use. And so you'll see what we mean as we go towards the end of this lecture. One of the things you're going to see a lot of in this lecture is set notation. And so this is just a reminder of what set notation is. So you'll recall that if we have a set X, then that set is defined as a collection of items or collection of things. And those things are usually described as X1, X2, all the way through to Xn. And the way that we show a set of individual things is using these curly braces, these curly brackets. The size of a set is given by, either the capital letter N or by what's called the cardinality, which is this absolute value of X. So when X is a set, the absolute value symbols describe the cardinality of the set, so the size of the set. And the last thing is to something that we're going to see a bit later, is that a set which has zero size, a set which has a cardinality of 0, is what we call the empty set or the null set. And the null set has this funny symbol of the 0 with the line through it. That'll come up a bit later, but just included here so that if you look back here for reference, you'll be able to see what we're talking about. Okay, let's dive in. So the first couple of concepts that we need to understand when it comes to probability is the concept of outcomes and the concept of events. So given any experiment, there's a number of possible results, possible things that can happen as a result of your experiment, and these are known as outcomes. A crucially important thing about the outcome is that every run of the experiment can produce one and only one outcome. Okay, and that's an important sort of definitional thing to understand. It'll also help when we're thinking about how we sort things into outcomes with different experiments a bit later on. The set of all possible outcomes is called the sample space. And the sample space is frequently given this symbol capital omega. I know that's a bit redundant with the capital omega that we've used for population earlier. But these two things are not ideologically dissimilar. The population being the set of all possible observations and the sample space being the set of all possible outcomes. So there is some overlap conceptually with these things. So this is, it's a nice way of thinking about it. One of the example that I'm going to use here of the sample space is taking something that we'll all be very familiar with, which is flipping a coin. Okay, so it's basically the simplest possible experiment that we can come up with because it has a sample space of size 2. And that is that there are two possible outcomes, one of which is that the coin comes up heads, and the other which is that the coin comes up tails. Now here I've provided an example of an Australian coin, which is useful because the head is literally a head and the tail contains literally a tail. Yes, so the sample space of this single coin flip is this, is the sample space is the set of outcomes, which is purely head with H and tail with T. Okay, if we toss the coin not once, but twice, and ask, or equivalently, if we were to toss 2 coins, then the sample space of possible outcomes increases. That's because now we're no longer just talking about a single head or tail. Instead, now there is 4 distinct possible outcomes of our experiment. Those distinct outcomes are head, head, tail, tail, head, tail. Sorry, I've got a typo here. Head, 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 tail, tail, head, and that should be tail, tail. This is a finite sample space of size 4, of cardinality 4. Let us consider now an experiment where the rules of the, or rather a game, where the rules of the game are that the game ends, the game ends when you throw a head and then a tail. So we have the question, what is the sample space of outcomes of this game? How many outcomes can there be of this game? And the answer is that the sample space of that particular game is essentially, well, not essentially, it is unbounded. And that is because the ordering that we can have is head, tail, and the game ends. Head, head, tail, and the game ends. Tail, head, tail, and the game ends, right? So the game ends whenever you see head, tail in order, okay? But you can have conceptually an infinite number of heads or equally tails before you get to your head-tail termination. And so this sample space is infinite in size, but that doesn't stop it from being valid. Okay, so an important quality of sample spaces is that they can be infinite, but still have totally valid interpretation, be totally tractable in terms of probability. Okay, important side note. So what we're going to do now is we're going to actually play a game of tossing a fair coin. And so what you can see here is I've created, so from a single fair coin toss, there's 2 possible outcomes, head or tail. We've already seen this. And if we perform this experiment n times, what we call n trials of our experiment, and we record the number of occurrences of each outcome A, where A is either a head or a tail. Okay, the frequency or the relative frequency of each outcome is the fraction of occurrences of A is the number of occurrences of A. So this here just means the absolute frequency of occurrences of A divided by the cardinality of N, well, the cardinality of all observations, which is the number of trials, N. And so we can actually perform this experiment in R, which is what I've done here. I've created a little animation here, which is my coin toss. So you can see the coin going up and down and then landing on a particular side. And what we're plotting here is the relative frequency of occurrences of a head and a tail. Now there's N in this particular animation is 15. So you'll see that it cycles back to having no observations at the beginning in a second. And what you can see is that the absolute frequency, this value here, as a function of the number of trials is constantly changing, right? So as you take more and more trials, the relative frequency of heads and tails changes. So here we're back at the start. So our first observation is a head. We have 100% representation by heads. We then get a tail and it drops to 50-50. Then another head, 2/3 to 1/3, et cetera, et cetera, et cetera. And so what we can do is we can, instead of plotting it like this, we can then say, let's plot the relative frequency of heads as a function of the number of trials. So every time I throw my coin, I add that outcome to the pile and I calculate the relative frequency of heads, which is just, well, we'll talk about this a bit later, but this is how we can formulate this. And it's the cumulative sum of well, let me explain it now. This is what's called the binomial function. The binomial function with this setup produces either a 1 or a 0 with 50% probability. So it's a perfectly fair coin, and it produces a 1 or a 0, 1 if it's a head, 0 if it's a tail. And what I'm plotting here is the cumulative sum of all observations. So if you get a 1, if you get a 1 or a head, it adds 1. If you have a tail, it doesn't add anything. And then this is divided by the running number of trials, and that gives us the relative frequency. So what you can see, if I look at the relative frequency of heads given the number of throws, it starts out, the first thing I threw was a head, so it starts out at 100%. I then threw a tail, and it went to 50%. I then threw another head, it went to 2/3, another tail, and then another tail, and so it drops below 50%, etc., etc. Now, one of the things that we can see here was that as the number of throws become large, and I mean very large, this is a logarithmic plot covering, 4 decades in value. So this is going all the way out to 1,000 and 10,000 tosses of our coin. But in the limit of a large number of throws, that the probability of finding, the relative frequency of finding a head approaches 50%. And that turns out to be important, because what that means is that we can formulate the probability of an outcome as being the relative frequency of that outcome after infinitely many trials, after a very, very large number of trials. And so that is the probability of the outcome A is equal to the relative frequency of A as the number of trials goes to infinity. And this turns out to be both the definition of probability, or looking at it in a different way, if you go from something which has a known probability, this works going right to left, which is to say that given a known probability of an outcome, the relative frequency of that outcome will approach the probability as the number of trials goes to infinity. And that's called the law of large numbers, something that we'll hear about a bit later. But given this definition, given this knowledge of what the probability of what the relative frequency does in the limit of large n, we can define the probability, and we can then immediately infer a couple of important properties of probability. The first of which is that because probability is derived as from a relative frequency, it has to have a value between 0 and 1. Okay? Because if every single observation is observation A, this ratio is unity, and it can't go higher than unity by definition, right? And it also can't go less than 0, because there's no such thing as negative counts in our experiment, in our relative frequency. The next thing that we can identify is that the probability of all possible outcomes. So the probability of A, of A1, A2, A3, A4, A5, or in our coin tossing lingo, the probability of heads and the probability of tails. So the probability of all possible outcomes. So that is that the outcome A is an element of the full outcome space, the full sample space. Because omega is the sample space of all outcomes, and because the probability is defined as a relative frequency, the sum of all relative frequencies has to be unity, has to be 1 by definition. So the sum of all probabilities of all possible outcomes has to be 1. It's another very important outcome, another very important property of probability. Okay. So far, we've been looking at, we looked at the plot of the probability as a function of n, and we looked at the running sort of relative frequency from our animation of what happens as I flip coins and I constantly tally up the results. One way that we can visualize probabilities, or rather visualize outcomes of a particular experiment, is using what's called a probability tree. And we won't go into a great deal of discussion about these right now, other than to say that if you start here, you can use the probability tree to construct the sample space of all possible outcomes. And that is to say that we can start with, for example, our first toss, and our first toss will be either a head or a tail. We then, and the probability of that outcome is 50%, because it's a fair coin in this example. We then toss the coin again, and we find that you can have a head or a tail, and the probability of that outcome is 50%. And that then gives us the possible outcomes of 2 coin tosses as being the sample space of all outcomes, and you find it by just traversing the tree. So to get to this outcome, we have head, head. So we end up with head, head, and the probability, which we'll get to more, is 25%. We'll get to why that is in a second. You have this outcome here, head, tail, tail, head, and finally tail, tail. Okay, and so that's the sample space. So you can use the probability tree to construct the sample space of possible outcomes. Okay. This becomes very, very unwieldy with very many sequential trials. I mean, if you imagine that we tried to do this for our coin toss here, which had 15 trials, or God forbid, 10,000 trials, you can imagine how unwieldy this would become. Okay, and so there are ways in which we can actually calculate these probability trees using the binomial function that I flagged earlier, but that's not something we're going to talk about now. It's something we're going to look at in a little while, a bit later. Okay, let's increase the complexity of our experiment a little bit. So we just looked at the toss of a coin. We looked at a fair toss of a coin, which has 2 possible outcomes: a head or a tail, 1 or a 0. If instead of tossing a coin, we now talk about rolling a die. Okay, everyone's familiar with a 6-sided die. I'm sure everyone's played a board game at some point in their life. And the outcome, the sample space of a fair 6-sided die is these values: 1, 2, 3, 4, 5, 6, with some probability that we don't know yet. We can actually simulate the roll of a fair die very easily using a function called sample in R. And that sample function basically says, I want to sample a value from the vector 1 through 6, which is the possible outcomes in my sample space. And I want to draw 1 sample. So I want to roll the dice once. And when you do that, you find that the first value that you get is the value 5. Okay, so we have successfully simulated the roll of a die. That was fairly easy. We can then simulate many rolls of a die by specifying that size ought to be, more than 1. Size might be 30, for example. But we now also need to specify an additional option, which is called replace, and replace needs to be true. Now, why that is because if we go down here, I can give you a simple demonstration of why that is. What the sample function is essentially doing is it is saying that I have a variable, a parameter space that contains my sample space omega, and it contains the values 1, 2, 3, 4, 5, and 6. And what's happening with the sample function is it is saying, I want to select 1 observation from my sample space. And so let's say that the first die that we rolled gave us the number 5. If we don't have the replace function, then what happens is that value is removed from the sample space. And the reason for that is because there are many cases, which we'll talk about quite a lot later, of examples where you have a sample space where you want an observation to be removed from the sample space. So a simple example is if we were, instead of observing a die roll, let's say instead that we were drawing marbles from a bag. Okay, and those marbles were numbered 1 through 6. If we were to draw the number, 1 out, then that number is no longer in, the marble is no longer in the bag. It has been removed from the sample space. Okay, and therefore any subsequent draw from the sample space ought not to include the number 1, unless we replace the number 1 back into the bag before doing the next draw. And so that's essentially what the replace function is doing. Okay, and so that's what I've got here. I've got just a thing saying that if we have we've got our bag full of marbles and we want to replace it into the bag before performing our next roll. And the other way of saying this, the other way of describing what I've just said about putting the marble back into the bag is to say that the second roll of the dice, or the second draw from the bag, doesn't know about the outcome of the first roll of the dice or the first draw of the marble from the bag. And that is an important distinction. It turns out to be very, very important for a lot of probability. And so if the outcomes of sequential trials don't know about one another, then those are what we call independent trials. Okay, so independence is a very, very important thing that we're going to talk about, for a little bit now. The outcomes of those roles are also what are called disjoint. Disjoint is a term that means independence when you're talking about collections of outcomes, which we'll talk about in a second. So if we now roll our fair dice and we roll it, 10,000 times, and we replace it every time because they're independent, and we look at the probability of rolling each number, then you have essentially an equal probability of rolling each number of a fair dice. Okay, which makes sense, right? Hopefully, we haven't said anything controversial there. If the dice is fair, you should see each number equally likely over a very large number of draws. That's for each individual outcome. What about now if instead of asking what is the probability of observing a single value, but instead we want to know the probability of observing a set of values? Okay, so let's say that we want to know the probability of rolling a prime number with a single roll of a dice. So this is where we introduce the concept of events. Excuse me. So an event is defined as any set of outcomes. Okay, so we can call our event, we call it this funny E, and our event for rolling a prime number is the set of all prime numbers that appear on a die. And the set of all prime numbers that appear on the die are 2, 3, and 5. Okay, hopefully not contentious. So the probability of observing the event A prime when you roll a particular die is the sum of the probabilities of observing each independent outcome that forms the set. So put into numbers, that is the probability of observing the event E is the sum of the probabilities of observing the outcome A1, A2, and A3, being 2, 3, and 5 respectively. If your event contains all possible outcomes, that is to say that if my event is I roll a die and I see a number greater than 0, for example, then the event space is the sample space. And because the event space is the sample space, the probability of the event is unity, as we said, a couple of slides ago. Because of these two properties, we can also then define the probability of observing any event that isn't E or isn't A. Okay, so if I define an event A, which is just say the number 1 on a die, then the probability of observing not 1 is what's called the complement of A, or the complement of the event. And that's just defined as, or rather by definition, given these two properties, the probability of the complement of A is 1 minus the probability of A, given independent observations. Okay. And the last thing is that given this complementarity rule, if the event space contains nothing, so if the event space is, well, if it doesn't contain any outcome that is valid, so there's no outcomes in my event space, then because of the complementarity rule here, and because the complement of the empty probability space has to be the full sample space, the probability of observing an empty set, an empty event, is 0. So the probability of observing the empty set is 0. Okay. Again, it's just a derivation that you make that turns out to be important if you want to understand how, we do probability math a bit later on. So what is the actual probability of observing a prime number when you roll a fair dice? So it's the probability of the event space E, which contains the outcomes 2, 3, and 5. So it's the summation of the outcomes, probability of seeing a 2, probability of seeing a 3, probability of seeing a 5. Because it's a fair dice, each of those are 1/6 likely. And so the probability of observing a prime number is just 50%. Okay. Again, hopefully not contentious. Okay, let's now ratchet up the complexity once more into the probability of rolling, the sample space of rolling 2 die. Okay, so now we're going to imagine that we're playing a game of backgammon or something to that effect, where you have 2 die and you roll them together. Okay, now each die has the same outcomes. Each is a fair 6-sided die with outcomes 1 through 6. So the sample space of the individual die doesn't change, but the sample space of the 2 dice roll is now the set of all possible ordered combinations, which are called permutations of the 2 die. So that is to say, the sample space we can construct by hand is 1 on the first die and 1 on the second die. Or 1 on the first die, 2 on the second die, 1 on the first die, 3 on the second die, etc., or 2 on the first die, 1 on the second die, etc., all the way through until we get to 6 on the first die and 6 on the second die. So this is the sample space of all possible outcomes. And you can imagine that you can imagine constructing this sample space in exactly the same way that we constructed this tree here, but with 6 possible outcomes at each junction. Right? You can also do this internally in both R and Python using a simple function. In R, the function is called expand grid. And what that function does is exactly what I just did here by hand, which is that it says, given a vector of possible outcomes, what is the set of all permutations of those 2 vectors? And so if I just do the expand grid of 1 to 6 and 1 to 6, I get this data set here, this data frame, where I'm rolling a 1 on my second die and 1, 2, 3, 4, 5, 6, and then a 2 on my second die, 1, 2, 3, 4, 5, 6, etc., all the way through to 6 on my second die, 1, 2, 3, 4, 5, 6. Okay, the utility of having this data frame, though, is we can start to do some interesting calculations. So given 2 fair die, the probability of observing any one of those outcomes is just 1 on the number of possible outcomes in my sample space, so the cardinality of my sample space, which is 1 in 36. But our game doesn't care about whether or not we get a 1 in the first die and a 3 in the second die, or a 3 on the first die and a 1 on the second die, because both of those things sum to the number 4. Okay, so for the purposes of our game, we don't actually care about the permutations themselves. We care about the frequency of seeing the event, my die, sum to the value of 4. Okay, and so instead of asking what is the probability of seeing any one outcome or any one combination of possible die rolls, we can then say, what's the probability of seeing an event, which we define as, here I've defined as the event, the sum is equal to 5. And what we can do is we can construct this event really trivially within R and Python, given this vector, this matrix that we just had of all possible outcomes. Because all we do is we sum the two columns of that data set, the data frame, and that gives us the sum of every possible outcome, right? We then take the histogram of all possible sums of outcomes, and what we find is this distribution here. And this should make sense, conceptually, because how many possible ways can you construct the number 2 with 2 dice rolls? Well, there is only one, and that is if you get a 1 on the first die and a 1 on the second die, right? There is no other way that you can construct the number 2 from 2 dice. Similarly, the same thing goes for 12. But how many ways can I construct the number 4, for example? Well, I can construct it with a 1 and a 3, a 2 and a 2, a 2 and a 2, or a 1 or a 3 and a 1, right? So we have the 1 and the 2 space, sorry, the 1 and the 3 is our first. We then have 2s, and then we have a 3 and a 1. Okay, so we can construct that. Those are the possible outcomes of our sum to 4. And this is why we get a peak at 7. 7 is the easiest number to construct when you have a roll of 2 die. And we can actually just demonstrate this. So we can use a really simple simulation, our simple simulation using sample of dice roll. So this bit here is just reproducing the plot I did here, the analytic probability of observing each outcome. And this section here, this second histogram that I'm constructing, is calculating the observations, the sum of random draws of dice where I've taken them 2 at a time. So the n column here is filling this matrix to be a two column matrix where each row is a random independent throw of a die, which is exactly the same as throwing 2 die together 1 at a time. And what we find is that the analytic probability with 10,000 throws, the analytic probability is the blue, and the observations are the red, and you see that while they're not identical, they are very, very similar. So we've verified that our analytic probability of seeing certain combinations of sums are the same. And what this thing is, what this relative frequency of seeing a particular value is, what we've constructed there is we've constructed a joint probability. Okay, that is the joint probability of observing or rather the joint probability of observing an event E, or in this case, the sum of 2 throws being a particular value. With any 2 die, we showed above that the probability of getting any outcome, because it is 1 on the cardinality of the sample space. So is 1 in 36 for 2 die, right? So the probability of me getting a 1 and a 1 is 1 in 36. The probability of me getting a 1 and a 2, or a 3 and a 5, or a 5 and a 3 is 1 in 36. That is true if and only if the observations are independent. So the last thing we're going to talk about in this lecture is the concept of independence and how important it is for inference in statistics, because there are very, very significant outcomes that happen when we consider the role of independence. So the definition of two independent variables is that they are independent if the probability of seeing A and B is equal to the probability of seeing A multiplied by the probability of seeing B. Okay, and we'll go through and we'll demonstrate when that is broken for non-independent observations next week, when we talk about things like conditional distributions. But for now, we're going to spend the last 15 minutes of this lecture talking about independence. And we're going to do this using two tests that we're going to do together, two surveys we're going to do together, two stories we're going to figure out. So the first situation that we're going to consider is around the importance that independence has when we're talking about modeling. So I want you to consider a case where you are on a jury in a criminal trial. Okay, the criminal on trial was identified by matching a DNA sample found at a crime scene to a database of many thousands of people. The probability of incorrectly identifying a person, given the DNA that has been found, is 0.01%. Okay. Said differently, the chance that a person was identified purely by chance is 0.01%. Okay, very small. There's 200,000 people in the DNA database. The police found a match between the DNA and this one person, and therefore took that person to trial. Okay. The prosecution then stands in front of you in the jury and says that this is damning evidence, because the probability that the DNA is purely there by chance is 0.01%. So there's a 99.99% chance that the person sitting in front of you is guilty. Okay? So that's situation one I want you to think about. Situation two is to do with independence and the way in which that has influence over trends of data. You're standing at a roulette table at a casino. So I'm guessing that everyone's familiar with what a roulette table is. It's a big circle with numbers on it and a ball that spins around the outside, and it eventually lands on a number. Now, this is a very fair casino, and in that very fair casino, there is only two possible outcomes of our roulette table. It lands on a red square or it lands on a black square within our roulette. Okay. Now, at the roulette table, there is a sign that is updated on the fly, and it shows the last 25 rolls, the outcome of the last 25 rolls of the roulette table, of the ball and what it landed on. And when you walk up to the table, the record shows that all 25 occurrences of the last 25 landed on red. Now, the table has an equal number of red squares and black squares. So you, knowing that the probability of landing on red and the probability of landing of black is exactly the same, because they have the same number of squares, the same number of possible outcomes, and the rolls are independent. So the probability of landing on red is 0.5, the probability of landing on black is 0.5. You know that given the law of large numbers that we just looked at, in the long term, the relative frequency of black and red should be the same. And therefore, you conclude that you ought to bet on black. That's the logical choice. Okay? These are our two outcomes, our two possibilities. So we're going to now have a very quick poll about our two outcomes. The first about our two scenarios. The first scenario is about modeling the DNA of this person on trial. I want you to tell me, as a juror, given what you have just heard about 99% chance, 99.99% chance of the person being guilty, whether or not you think that the person is guilty or they are innocent. So again, we'll wait until we have sort of, 17 or 15 odd votes. So we're at 5 at the moment. Okay, we're at 11, nearly there, and it is quite evenly split. So we do need to get those votes in for the last few people. If you haven't voted yet, please do. Okay, 12. We'll wait for one more because I think that'll mean that we have a definitive decision. There we go, 14. Excellent. Okay, thank you very much, everybody, for voting. So we have 16 votes in, and the guilty verdict has taken it. Now, for those of you who aren't familiar with criminal law, you would have to all agree on the outcome. So if you actually were a jury, you 16 folk, then you would probably have a very long night ahead of you arguing over who was correct and who was not. But fortunately, I'm also on the jury, and I'm going to tell you what the correct outcome is. Now, let's look at the second thing. We have bet on. Are we going to, given the fact that we have seen 25 red observations in a row, are we then going to bet on black or bet on red? Okay. Okay, this is looking good. We've got 11 votes in so far, 12. We're about even, red and black, 58% to 42%. We'll wait for one or two more to come in. Last couple. Here we go. Okay, so we're basically 50-50 here, which is really good. It's really interesting. So we've got almost, I mean, there's a slight preference for betting on black, but it's not significant. You'll note that I intentionally gave you only those two options. I didn't give you the option to say it doesn't matter, and we'll see why that is in a second. We have a question. Do we have any information if other persons were identified by DNA? So this particular scenario that I'm giving you, at least one, well, we'll talk about it in a sec, but let's, for this argument, we're saying that one person was identified. But what we're going to do now, and it's a very good question, what we're going to do now is we're going to look at whether or not that's deciding that that person is guilty or innocent is justified. So the question that we really want to ask, that we really want to know, is what is the probability that we observed at least one match in our database purely by chance? Now, this is a worst case scenario than what we've given, because I'm saying at least one, because we saw one. Okay, so I don't want to ask what's the chance of finding exactly one. I want to know what is the probability of seeing at least one, because that's still in the event space that I'm witnessing. I've seen one person who's been identified, and therefore I want to know what the probability that happening is, at least one. And the probability of there being a chance match in my database is from our complementarity. It's 1 minus the probability of us seeing no chance match in the database. Okay. Now the probability of us seeing no chance match in the database is the probability that we don't match by chance with the first person in the database, and we don't match by chance with the second person in the database, and all the way through to the 20,000th person in the data set. The probability, we said, of incorrectly matching DNA to a random person is 0.1%, 0.01%. So the probability that I match by chance is 0.00001, 0001. And therefore, from our complementarity again, the probability that I have no chance match is 99.99%, as we said. So I then take the probability that I don't match by chance with person number I, and I put this value into my probability calculation here. Okay, so I take the number 0.9999 and I multiply it by itself for the first person in the database, and then the second person in the database, and then the third, the fourth, the fifth, all the way through to the 200,000th person in the database. And that summation, that geometric sum, gives me the value 0.14, which means that there is a 14 or 13.5% chance of not finding at least one pure chance agreement between the database, between the DNA on file and the database that we have queried. Put another way, there is an 86.5% chance that the match that we see is purely random. Yeah. And the reason why our intuition is so, like, why so many of us intuitively think it's a 99.99% chance, basically one, therefore it has to be correct, right? Is because we don't think about it in terms of the number of trials, the number of independent trials that are taken. Okay, we don't think about it in terms of the fact that it's not just we queried this one person and that one person was the one that we found. Instead, we've queried 20,000 people and we've only waited until we find the correct answer. Can't we just calculate the expected number of chance matches in the database by doing 200,000 times 0.001? Yeah, that's one way of doing it. Yeah. This is asking a different question. That's asking what is the number of chance matches that I expect, right? But we were more interested in asking what's the probability that given I saw a match that it was by chance. It's a slightly different question, but absolutely totally a valid way of doing it. Yeah, and there's no problem with computing it that way. Yeah. Okay, so given this, I would imagine if I now went back to our poll and gave you the option to do a do-over, that the majority of you would probably say, I'm probably less confident in that person being guilty, given that there's an 87% chance that it was purely random, I guess. Okay, clear that. And I'm gonna, okay now. Okay, so that's the first one. What about the second one? So the second, I wanted to close that poll. Yes, good. And the second thing that we were discussing was the rolling, the roulette table. And this is going to be, yes, this is going to be where we end for today. So we're almost right on time. So looking at the roulette table, this is where we come across an important statistical thing, which is known as the gambler's paradox. So the gambler's paradox, or a statistical paradox, is something that we're going to see quite a bit of in the course of this lecture series, mostly because I really enjoy them, but also because they're very, very important to being able to fortify our own intuition to statistical sort of anomalies. The gambler's paradox basically proceeds like this. We have observed 25 red observations. And what we have said, by preferencing voting for black in the next roll, what we have said intuitively or in our own heads is that I've observed 25 red occurrences. The probability of me seeing 26 red occurrences, red rolls in a row is 26, is the event space of 26 reds, which is 0.5 to the power of 26, which is a tiny, tiny, tiny number. The probability of me seeing 26 reds in a row is minuscule. And therefore, it makes sense that I should vote on black. I should bet for black. Okay? The problem is that this probability that we've just calculated is not the relevant probability to look at. And that's because observing 26 reds in a row, you're absolutely correct, is very unlikely. But observing 25 reds and then one black is exactly as unlikely as observing 26 reds in a row, just from our probability, right? Because it's 0.5 to the power of 25 plus, or sorry, times 0.5, right? So the probability of observing red, 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 or watching or seeing red, 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 black is exactly the same. It's equally 0.15. And that's because what this value is, what we just calculated up here, is the probability of seeing the outcome 26 red, given we haven't observed anything yet. Okay? But that's not the situation we find ourselves in. We have observed 25 red. And what we've implicitly done by doing this computation at the top here is we've assumed that the universe knows and cares that we saw 25 red. When in reality, the universe, because these are independent observations, does not care about whatever came beforehand. The probability of the next roll is equally 50% and 50%. Just like we saw in our probability tree, right? Where each junction had the same probability, 50% and 50%. And so this number is essentially the summation to find, or the multiplication to find that particular outcome. But once you've observed the throws, the 25, they become completely inconsequential to the outcome of the next throw. And this is one of the important things that, one of the important outcomes of independence that we as humans fundamentally have trouble with. Because our brains say, well, yes, the probability should be 50-50, but I know that the law of large numbers says that in the long run, this is going to go to being 50-50 jointly. And so there's a greater probability of the next one being blue, because otherwise we're not going to even that score. But the reality is that each observation is completely independent, and therefore there's no preference one way or another. And so if we take one more spin, turns out that the next spin was actually a red. And if we had have come to the table now, we would have seen 26, or still seen 25 red in a row. And so that's the gambler's paradox. So these are two statistical paradoxes, or statistical outcomes that happen because of the way in which our intuition doesn't work very well when it comes to independent observations, particularly when the number of outcomes is large, i.e. when we have something that is, arbitrarily uncommon, but is applied to many, many, many trials, like we saw with the DNA database, or when we implicitly assume that there is some non-independence or lack of independence between our observations by looking at previous outcomes, like we did in the gambler's paradox. We were essentially applying a sense of memory to our outcomes when, because they are independent, absolutely no memory exists. So that's those are the things, that's where we're going to end today. Next week, we're going to start by talking about the next type of probability, which is non-independent probabilities, what we call conditional probabilities. And this is going to open up a whole new realm of paradoxes and things, which we're really looking forward to talking about. If people have any questions, as always, you can feel free to ask those questions on Slido or on the Moodle. We're going to end today, as I said, by asking a one more poll, and again, obviously independent, so please be truthful, lest you end up sit here and being stuck with an outcome you don't want. Whether or not you thought that the interactive portion of the lecture that we just had was useful and interesting and a nice way to stay engaged. Yeah, please vote. And if you have any questions, you can feel free to add them to the Slido or speak up as you would like. And otherwise, once you've voted, please feel free to sign off. And that's all for today. Thanks very much, everyone.
Bye.
Bye.
Thank you. See ya.